Welcome back, everyone. Before we get into new material, since this format is new for all of us, I thought it might not be a bad idea just to do a brief review of Chapter 6, which we started talking about before the break. And I think it would do no one any harm, myself included, just to go through this material again and explain it once more. So Chapter 6 is about one major reaction type that alkyl halides go through, which is known as nucleophilic substitution. And here is a scheme for a typical nucleophilic substitution reaction. Remember that whenever we have a substitution reaction, there's two pieces in the starting group molecules that, if you will, switch places. And that's exactly what happens here. This group X, which is usually a halogen, doesn't have to be. There are other leaving groups, but I think that's what you'll mainly be running into. So the so-called leaving group and the nucleophile wind up switching places, and you get this nucleophilic substitution product of this type. And there's also, in general, small and organic side products that I, in general, don't care about, but OWL sometimes does, so be careful. Be sure to read the directions for OWL assignments. They sometimes want you to show those things. I think they're pretty irrelevant, at least in comparison to the major organic product and the importance of it. Now, again, bear in mind that the carbon atom that's attached to the halogen in all cases needs to be sp3 hybridized. So reactions of this type do not occur for aromatic halides and do not occur for vinylic halides, in which the carbon atom is sp2 hybridized and involved in a carbon-carbon double bond. Those types of carbons form bonds with halogen that are much too strong for this type of reaction. So it does need to be sp3 hybridized. But, of course, there's multiple flavors of these starting materials, or these substrates, as we call them. And whether that substrate is primary, secondary, or tertiary, or I should say methyl primary, secondary, or tertiary, will strongly affect the type of reaction that we can get, and the type of reaction, even more importantly, that we're not going to get. In the case of these starting materials being methyl or primary, the so-called SN2 mechanism of nucleophilic substitution is going to come into play. So SN2 stands for substitution nucleophilic bimolecular. And this term bimolecular means that the reaction is going to involve two different species in the rate determining step. And so as a result, the rate law of the reaction, which I think you covered rate laws, however briefly, in Gen Chem, the rate law is going to be second order. We're going to see two terms in the rate equation. The mechanism of a typical SN2 reaction is very straightforward. Here I'm just using as an example 1-iodopentane and the cyanide ion. Here we're given sodium cyanide. It could just as well be potassium or lithium cyanide. The identity of the alkali metal cation is irrelevant. The alkali metal cation is what we call a spectator species. It's not going to play any role in the reaction. And I believe I've mentioned this, but I think it bears repeating. I like that term spectator ion because for once, it perfectly describes what's actually going on. The Na plus ions are still going to be there, but all they do is float around and watch. They don't play any role in the reaction at all. That's why you don't see it mentioned here in the mechanism. But to show the mechanism, we'd simply draw a curved arrow from the nucleophilic atom of the nucleophile. In this case, it's this carbon atom. So remember, the structure of the cyanide ion is a minus charge in the carbon atom. It's essentially a carbanion. And so, as we put it, that anion will attack the carbon that bears the leaving group and kick out the leaving group, break the bond between carbon and the leaving group atom, in this case, iodine. And both of those things will happen at the same time. There's no intermediate. It happens all in one step. And I know I talked and hemmed and hawed a little bit before break about the transition state being planar, and all that is true, but it leads down various rabbit holes that I really don't think are worth us pursuing. I would like you to be aware of two things, I guess I would say. Number one, that transition states are not real species. They're not something that we can detect experimentally. There's not like a thing between the 1-iota-pentane and the hexane nitrile over here, which is the product. There's not a thing sitting in between them that we could detect if we tried. Rather, the reaction is what we call concerted, meaning it happens all at once. The nucleophile attacks the substrate, the leaving group leaves, both at the exact same time, and there's no reactive intermediate. We go straight to the product. And thus, the rate law for an SN2 reaction will look like this in general. It'll be rate equals rate constant times substrate concentration times nucleophile concentration. And thus, changing the concentration of either of those species will affect the rate of the reaction, will affect how fast it is. And no wonder that's the case, because when we look at the mechanism of the rate determining step, well, first of all, how do we know what the rate determining step is? Well, there's only one step. So by definition, it must be rate determining. And if you look at what's going on here, there are two species that are involved. Both the nucleophile and the substrate are involved in that step. And so that's why the rate law is second order, and both the substrate and the nucleophile show up in the rate law. So if we were to write the rate law for this particular reaction, it would say rate equals rate constant times 1-iota-pentane concentration times cyanide ion concentration. Or you could just as well write times sodium cyanide concentration. Same thing, because the sodium ion doesn't play any role here. Now, in terms of stereochemistry, what happens if the starting material is chiral? In this case, it's not. 1-iota-pentane is not a chiral molecule. But we did an example where the starting material was chiral. And what we find is that an SN2 reaction will go with 100% inversion of configuration at the reacting carbon. So if the reacting carbon starts out in the R configuration, in the product it will be in the S configuration. And if it starts out in the S configuration, in the product it will be the R configuration. 100%. In fact, you could almost say that the definition of an SN2 reaction is one in which there is 100% inversion of configuration. So that's pretty much what we said. We also went over the energy diagram, and I think you have that already in your class notes. So that's one type of nucleophilic substitution reaction. What about if the starting material is not methyl or primary, but rather is tertiary? Can we do a nucleophilic substitution reaction there? Well, yes, we can, but it doesn't go by an SN2 process. It goes by what's known as an SN1 mechanism. And again, that would stand for substitution nucleophilic unimolecular. In this case, the reaction mechanism of the substitution itself has two steps. That, by the way, is something, maybe it's just me, but it's something I always found kind of confusing about nucleophilic substitution reactions, is to remember that the number in the name of the reaction, SN1 and SN2, does not tell you how many steps there are. It tells you how many molecules are involved in the rate determining step. So that's right, the SN2 mechanism is one step, the SN1 mechanism is two steps. So it's not talking about the number of steps in the reaction mechanism. It's talking about the number of molecules that are involved in the rate determining step. And here, this would be a typical SN1 type reaction. We'll take 1-chloro, 1-methyl cyclohexane rather. And if we were to dissolve this up in methanol and heat it, usually these are endothermic reactions. They generally require heat, or at least go much faster when heated. And again, I'm just using methanol as an example. I could have used any other oxygen or nitrogen nucleophile, but it's very typical with an SN1 reaction for the nucleophile and the solvent to be the same thing. And so the first step of any SN1 reaction involves the leaving group just leaving. Nothing, it's not assisted by anything, nothing makes it leave except insofar as the polarity of the solvent is involved. And you'll notice what you get when you're done with that is a carbocation. So that's a species where the carbon has 3 bonds and no lone pairs. If you work it out for the formal charge will be +1 in cases like that. And whereas we started with an sp3 hybridized carbon, which is tetrahedral in shape, carbocations are sp2 hybridized. So that's something you'll need to know about them. And what that means is that this species is planar at the carbocation carbon. It's flat. And thus, the methanol, our nucleophile, our nucleophile and our solvent, when it attacks our carbocation, it can come either from above the carbocation or from below the carbocation equally well. And so when it does so, that means that if the starting material was chiral, that means that our product is going to lack optical activity. So even with an optically active or chiral starting material, the product will be optically inactive. That doesn't mean that the molecules that we get at the end are no longer chiral. They are. It's just that we will get a racemic mixture, at least in theory. The truth about the SN1 mechanism is a little bit more complicated than that. And in fact, in real life, we generally don't get exactly a racemic mixture. But again, I don't think these details are too important for our purposes. Theory would certainly predict that you'd get a 50-50 mixture. So if you started with one, this again is not a chiral compound. I think we showed in class an example of a tertiary substrate that was chiral. And then even if you start with 100% pure R, our product will be 50% R and 50% S. So you'll get both. Again, that's because the nucleophile can come from either side of that planar carbocation. And so after our nucleophile / solvent attacks the carbocation, we get a species like this that typically is going to have a plus charge. And so at this point, I do want to stress the SN1 reaction itself is over. The nucleophilic substitution is done. And that substitution takes 2 steps. First, the leaving group leaves, which, by the way, is the slow step. And so that's the rate determining step. It's just another way of saying the same thing. And so no wonder the rate law of an SN1 reaction is first order. The only species that's involved in the rate determining step is the substrate, not the nucleophile. The nucleophile is not involved in the rate determining step. And so changing the amount of the nucleophile, which again is going to be in general one and the same as the solvent, will not change the rate of the reaction at all. That doesn't affect the speed of the reaction. Only the concentration of the substrate is going to matter here. So again, after our nucleophile attacks our carbocation and we get this species, and this, by the way, is very fast compared to this step, perhaps unsurprisingly. This way we get rid of the plus charge in carbon. But we get this type of intermediate here, with in this case, a plus charge in oxygen, so we need to get rid of that plus charge. And again, I do want to stress, and by the way, your book is very good about this. Your book does a lot better job than most organic textbooks I've seen in showing the energy diagram of a typical SN1 reaction. The only thing is, I just want to be clear that at this point, the actual SN1 reaction is over. But we do need one more step in order to get rid of the plus charge on this species. And so we're going to do that by pulling off this proton on that oxygen. And that will get rid of the plus charge and we'll get a neutral product. It's important to know that you always want to aim for a neutral organic compound as your product. I'm hard pressed to think of any exceptions. So in general, that's a good rule to aim for. You want to aim for a neutral organic compound. Now, how do we know to use this methanol molecule as our base? Well, when we look back at what we're given, we see that there is nothing else. There's nothing else around that could in principle act as a base. So we need to be careful in our mechanisms to show only species that make sense and match what it is that we're given. So I'm not given OH minus. I don't see CH3O minus or any other such species mentioned here. And we also know that methanol is an extremely weak acid. It's not going to spontaneously break up into CH3O minus and H plus, at least not in any reasonable concentration. Maybe one molecule in 10 to the 20th molecules will do that, but certainly not enough to use that in our mechanism. So that leaves only a neutral methanol molecule itself. Remember, alcohols are amphoteric, like water. So they can act as either acids or bases. And here, this methanol molecule is acting as a base. And our major organic product will be this methyl ether that you see here. And yes, there are inorganic side products as well. Generally, we don't really care about those, or at least we care about them so much less than we care about the major organic product that we don't even generally mention them, except for owl. Keep an eye on owl. So other than that, I think that's a good summary of nucleophilic substitution. And so with that, we can leave that behind and move on to new material in chapters 7 and 8. So I'll see you then.